Welcome everyone to this lecture where we're going to discuss dealing with outliers in your data set. Often a data set from the real world is going to have a few points that are extreme outliers. If we think back to the housing data set we're going to be working with, something that could be an outlier is just a very large house. There's going to be a few very large mansions in your data set, and it's often better to simply remove these few points from the data set in order to have a more generalized model. That way you can just have a caveat to your model saying this model is not meant for houses that are likely to cost more than, let's say, 10 or $15 million. So what do we actually need to consider when we're talking about outliers? We'll need to talk about what we're actually defining as an outlier. And that takes into consideration two main components: the range and limits of what you're calling an outlier, as well as what percentage of data you're willing to refer to as an outlier. And keep in mind, pretty much everything we're going to be discussing here is extremely domain dependent and extremely dependent on your exact data set. There is no one-size-fits-all solution. And sometimes it would make sense to, even if you have extreme values, keep them in because they're actually going to be representative of maybe upcoming future information if you can see a rapid change in whatever industry your data is in. So again, there's no 100% correct solution on how to actually deal with outliers. We're just going to present a few different methods that you can refer to in case you find yourself experiencing outliers in your own data set. So let's first talk about range and limits. How do we actually decide on the range or limit of a value to then declare it an outlier? There's many different ways you can do this. There are more mathematical ways, such as using the interquartile range. Recall when we discussed box plots, that was the IQR. So if you think back to the box plots, we actually had little dots that were labeled as outliers. And recall that methodology basically said that either you're 1.5 times IQR below the first quartile, that is Q1, or you're 1.5 times IQR above Q3, your 75th percentile, and anything beyond that limit is going to be your outliers. I would refer you back to the box plots to a deeper discussion on interquartile range and what constitutes an outlier there. You should keep in mind that this is not a 100% set in stone thing. You may want to extend a little bit beyond IQR. You could set your own limits like 2 times IQR, 3 times IQR, depending on the distribution of your data set and your exact situation. You could also base it more on standard deviation. So maybe anything beyond 3 standard deviations of your data set is going to be labeled an outlier or something like that. And this really helps when your data is going to be normalized. So if a particular feature looks like it's following a normal distribution, standard deviation could be a reasonable assumption to make as far as choosing something that is an outlier that you want to just kick out. Or kind of the easiest but more art than science way is to just make a visualization or a scatter plot, or just choose a domain limit value. Maybe you're working on the housing data set and you talk to your real estate agent and say, what is a good reasonable range for an upper limit on the price of a house? And maybe they say, well, $10 million should be your upper limit. Anything beyond that, a model is not really useful. It's more up to a person to look at the marketplace and talk to individual buyers. In which case, you're just going to say, okay, anything in my data set above $10 million in price historically is just going to be booted out as an outlier. Lots of different ways you can do these considerations for range and limits of outliers. Now let's talk about the percentage of your data. Keep in mind that if you're using some sort of mathematical methodology, or even a visual one or domain one, and a large percentage of your data is being labeled as an outlier, then they're not really outliers, because outliers, almost by definition, are going to be things that are extremely different from the rest of your data. So you shouldn't be using a methodology that suddenly labels 10% of your data points as outliers. Really, that just happens to mean that you have a wider distribution of your data rather than just a few outliers. So you should probably keep in mind that you're going to limit outliers to just a few percentage points of your data at most. So that is to say, if you have 100 total rows of data, you shouldn't be labeling 25 of those points as outliers. Instead, you should look back at your data, look back at the domain situation, and really think about what is happening here that you have such a wide distribution of your data. In that case, you're probably just going to have to make a very generalized model. Okay. So finally, we want to utilize visualization plots. They're extremely useful when we're talking about outliers, especially things like scatter plots, where we're able to directly see and identify outlier points. And you should keep in mind, this will create caveats for your future model, as we already discussed. If you don't train your model on any houses that are above $10 million, and a new house comes on the market that is going to be priced probably at above $15 million, you'll just have to be reasonable and say, my model is not going to be able to predict the price of this house. It's too large. We're really not suited for it. So often when you're setting limits based off something like a range or domain knowledge, and you already set those limits on previous historical trained data, those limits are going to have to stay in place for future incoming data. Okay, and as I've kept saying, there is no 100% correct outlier methodology that's going to apply for every situation. Let's explore the Ames dataset we're going to be working with and see how we could explore how to remove outliers and how to identify them. I'm going to head over to the Jupyter Notebook now. All right, here we are at a notebook. I've already gone ahead and imported NumPy, Pandas, Matplotlib.pyplot, and Seaborn. What I'm going to do is I'm going to copy and paste a function that is in your lecture notebook that goes along with this lecture called dealing with outliers. And it's essentially a function that allows you to create a random distribution of ages. So what I have here is I've created this np.random.seed. And then what we do is we just create a normal distribution, and you can actually affect the mean you want, as well as the standard deviation, and the number of samples, and the seed itself. So what this does is it creates a normal distribution centered around 50 by default, standard deviation of 13, and then it rounds all the ages so that there's no decimals. And essentially, then it returns that sample of ages. So when you run this, if I say sample is equal to create ages, run that, and then check what's in my sample. I'm going to zoom out one level so you can see it. It's just a list of random ages here, normally distributed. Whether or not a set of ages should be normally distributed, that's kind of up for debate. It actually depends on the country. Some countries are more uniform than others, but the main idea here is just to get a nice little data set so I can show you a couple of ways to try to identify outliers in this. One definite way is to just first check out the distribution of your data set. And we have lots of tools for this. We already know I can do something like this plot, just pass in the sample itself, and if you run this, it will show you the distribution. And you can also affect the number of bins in case you want to try to get a little more detail here. So I could say 20 bins, and it looks like we may have not exactly outliers, but more people who are closer to 70 than what should be expected, given that I did actually create this as a normal distribution. However, in the real world, we wouldn't really know that. What I want to make clear, though, is given this sort of data set, if you do end up kind of randomly generating something like this, or you get a real-world data set that looks like this, we cannot just say that everything on 70 and kind of everything below 20 is an outlier. We should be using some sort of more robust methodology for that. Something you could do as well is create a box plot for this. So it could say box plot, pass in sample itself, and it will create a box plot. And you'll notice that using the IQR methodology that a box plot follows, it does actually create a outlier dot. Keep in mind, there is possibly a warning here where it's actually telling you you must say data is equal to sample. So if you're running a future version of Seaborn than what's shown in this video, you'll get this warning. Keep that in mind. It's not a big deal. It's just telling you you have to say x is equal to or data is equal to, etc. So it's just about arguing the position versus just passing in sample. Other than that, we can see here that it looks like based on 1.5 times IQR, we do have an outlier here. So what if we actually wanted to do this mathematically and grab this particular value or filter out this particular value? How can we do that? If we have a Pandas series, let's go ahead and create that. We'll say series is equal to PD series of my sample, which means now my series is organized as so. What I could then do is call describe on this and begin to explore the IQR range. And recall, IQR is essentially the range between the 75th percentile and the 25th percentile. So then that means I could do something like the 1.5 times IQR. So I can then define IQR as equal to these particular numbers right here. So I could say 55.25 minus, let's see, 42. So we'll grab that there. And then if you're looking for values either below or above, kind of depends on what we're actually looking at, I could say my lower limit is equal to 42 minus 1.5 times IQR. So then my lower limit age, in this particular case, looks like to be 22 years old. And if we take a look at this particular data point, it is less than 22 years old, which is why it's outside of this whisker. You can see that whisker is essentially right up the 22 age mark, and that is an outlier. So this is kind of a manual way of doing that. And later, if you wanted to, you could say, okay, give me the series that is over the lower limit, and then you can begin to start doing it that way. So then you could say series where series is above lower limit, run that, and notice our length is now 99. We essentially got rid of that one person. And that's a totally legitimate way to get rid of an outlier. You could also base this on many other mathematical methods, like some sort of standard deviation away from the mean, etc. You might be wondering, as far as IQR, do you have to call describe every time? Is there a more programmatic way of doing this? And luckily, NumPy actually comes with a percentile call. So what we can do is, if you take a look at np.percentile, you'll notice it takes in A, it's a little strange, but it takes in A and Q parameters. And it's going to be the qth percentile, and essentially you can pass in a list of percentile values, and A is the array you're actually analyzing. Essentially what that means, if I wanted IQR, what I could do is the following. I could say, all right, here is my sample, and then give me the 75th percentile and the 25th percentile. You run that, and it will return them to you as an array, 55.25 and 42. Or you could just pass in one of these, 75, and it will give you the 75th percentile. So this will now allow you to do this programmatically instead of having to call this describe method every time. So you can now easily see that I'd be able to do something like 25th and actually label these as Q75, just tuple unpacking here. Q25 is equal to this tuple or list that's returned, and then I actually have those values. And then programmatically, what I could say is just IQR is equal to Q75 minus Q25, and then you're doing the same thing. So now you don't need to call describe. This will just work. You just pass in the sample itself. So a little less work for you and a little more robust. And recall, we were doing 1.5 times IQR, and then if you also want the lower limit, so then that's Q25 minus 1.5 times IQR, 22.125. So here you can see the limits. All right, so obviously there's many different ways we can deal with outliers. A lot of this can be just trimming off some sort of limit here, and you could just run a for loop for all your features and just remove everything based off something like this. Now, another way to do this, which again is going to be more dependent on your actual domain knowledge, is to do a visualization and take what you already know about the domain and affect it that way. So what I mean by that is we'll actually read in our data set. So I'll say df is equal to pd.read_csv, and inside of the data folder, so if you go outside of feature engineering, there's actually a folder called data, and then there's the original Ames housing data.csv. You'll notice that there's actually a lot of different CSV files here. One is where we've removed outliers, one is where we have missing data, one is the final df, etc. You should just be selecting housing data CSV. And be careful not to overwrite this, otherwise you'll need to download the zip file again. This is the original housing data. What we're going to do throughout these lectures is slowly make changes to it until we have this final data frame. So let's imagine that I do have some domain experience in the housing data set. And what I want to explore is really the label that I'm trying to predict. And the label in this case is, if we take a look at data frame and scroll, I think it's all the way over here on the right, is the final sale price. Essentially, I want to know the prediction for the sale price given all these features. That's my main goal way later down along the line. What I should do is immediately check, are there sale prices that are historically just way out there? Are they outliers? And what I could also do is begin to explore this against features that are highly correlated to the label. So what I can say is something like df correlation, run that. This will give you a very large data frame showing you every single feature's correlation with every other feature and the label itself. But I'm probably only really now considering the correlation between all these features and the actual label I'm trying to predict, which would be sale price. So if we run this, essentially what this is every single feature's correlation with the sale price. Let's actually sort this so I can see which features are most strongly correlated. So we'll say sort values, run that, and I can see that as far as positive correlation goes, overall quality is the highest positive correlation to the sale price. Obviously, sale price is going to be perfectly correlated with itself. It makes sense that something like overall quality of a house is going to be highly indicative of the sale price. So let's go ahead and just do a scatter plot of overall quality versus sale price. So I'm going to say SNS scatter plot, x is equal to overall quality, and we'll say something like y is equal to sale price, and let's have data equal to df. And so we essentially get something like this. So right away you'll notice that it doesn't look like a typical scatter plot. You actually see these lines, and that's just indicating to you that there's essentially a precision of 1 with overall quality. So your overall quality is some rating looks like between 1 and 10. So it's 1, 2, 3, 4, etc. Now just from this, I can actually detect that there appears to be a few points that are outliers themselves. And what do I mean by outliers on this particular plot? I mean that clearly I can see as quality goes up in score, so does the sale price. There's a distribution within each of those. Not every house is created equal and within a certain quality score, but clearly the lower quality, the more likely you're going to have a lower sale price. But you'll notice that as we continue along this, there are a few houses that seem to kind of buck this trend. Specifically, I'm talking about maybe if you take a look at these 3 houses, they're selling at a price that is more indicative of a much lower quality. So they're rated quality-wise as like a 9 or even a 10, but their sale price is looking to be right in the middle of the pack for something that would typically have a quality of 5. You can also see that there's some houses here that are also outliers on the other end of the spectrum, selling for way more than what you would expect for something's quality. As you get to something like quality of 10, you'll notice the distribution gets much wider. So whether or not these 2 points are indicative of outliers is a little hard to tell. Essentially, these are kind of really large mansions that are probably have extremely high quality, which makes sense that they're selling really for a lot of money. What doesn't make too much sense is that something is a quality of 10, but also selling at a much lower price. So we'll go ahead and take a look at other features, like let's say this living area feature also seems to be highly correlated to the price, and let's do a scatter plot of that. I'm going to say SNS scatter plot, x is equal to this living area feature, and y is equal to sale price. And hopefully by now you can kind of tell why domain knowledge is so important. So now, if we just do this plot, we start to see those houses that we were earlier talking about. These 3 houses right here, these 3 points, are indicative of a much lower sale price, but with a very high living area. And that's probably these 3 points right here. We can't actually know for certain. We'd have to look at that closer. And I can do that with pandas. So what I could do is say something like, give me data frame results where df overall quality is, let's say, greater than 8. And recall we need to do an ampersand here, parentheses. The sale price is, let's say, less than, I think the limit around here is 200,000. So let's go ahead and type that out, 200,000. So you run this, and you see that we have 4 rows where that happens to be true. So there's 4 rows looking back here that are having some sort of really high quality, but the sale price is much lower. Whether or not these are reasonable houses to actually put into our data set really depends on our domain experience. But we can just tell, based off the scatter plots themselves, that these are outliers on not just 1, but actually 2 features, where they're just really large houses with very high quality that for some reason are at a bargain price. And that's exactly the kind of outlier you don't want in your model. It's not that bad to have extremely high quality homes that are also selling for very high prices, because that's a intuitive trend. And obviously if we start building a linear model, it's going to pick up on the fact that higher quality, larger house, greater amount of living area is probably going to be indicative of a very high sale price. These 2 particular houses probably sold more expensive than maybe what was reasonable, but they are following the overall trend. What is really going to screw up our model is if we have something that is an outlier of this fashion, where it's really not following the trend. These are 3 really high quality homes, and they have really large living areas, but for whatever reason, they happen to sell at a very low value. And this is the exact sort of outlier we want to be removing from our data set when it comes to building an effective machine learning model. These sort of outliers are really going to screw up the model's ability to generalize to the relationship of either higher quality, higher price, or higher living area, higher price, etc. And that's why you can use this sort of correlation as kind of a backstop guide to see what is an outlier and what is not an outlier. And keep in mind, this is a huge data set, so it'd be kind of unreasonable to do this all on your own with just doing this one by one for each of these features. Instead, we're just looking for a few points that are really going to screw up our model a lot. And you can do this by just checking out what is highly correlated to the actual label you're trying to predict. So you'll notice that in this particular case, it looks like I'm only looking at 3 houses that are just really bad houses for our model. Let's go ahead and remove these 3 houses. Earlier, we did report back that we saw there was kind of 4 houses that were a little suspicious, but probably the main ones that we need to remove are these 3 outliers. So just really going to screw up our model because they're quite an aberration across the particular relationship between living area and sale price. And it's very likely that it's also these 3 dots right here, and we can confirm that with Pandas by filtering out further. But let's go ahead and explore that. Notice I have these IDs. What I'm going to do is the following. I'm going to say, give me the data frame values for the data frame where, in this case, I'm going to say GR living area is greater than, if we come back here, let's say greater than 4,000. That kind of seems all 3 points are above 4,000. So greater than 4,000, and then we'll say ampersand df, and what I'm going to say here, where the sale price, and let's just say where the sale price is less than 400,000. So I can already tell based on my scatter plot, if we have a house where the living area was greater than 4,000 units and the sale price for some reason was less than 400,000, it's just way off the relationship we expect because we're giving actually quite a lot of leeway in that sale price limit. So running this, you'll see we're essentially getting the 3 rows here. And it's 1498, 2180, 2181, and those houses are actually represented here as well. 2180, 2181, 1498. You'll notice one of these houses is not present, 1182. It's kind of up to you whether you want to drop something like this. It's not one of these 3 points. It's somewhere over here. That is probably not too bad. It's just these 3 points that are really going to screw up our model. So what I'm going to do, and this is where it's more of an art than a science, is choose just these 3 points to drop. So let's go ahead and grab those index values. What I need to do is just say dot index. And so now I have this index. Let's go ahead and call this my drop index. So those are the 3 index points that I want to drop. And then what I'm going to do here is just say df is equal to df.drop. And I'm going to say the index, the drop index values, and I'm going to specify along axis is equal to 0. So that's essentially redefining my entire data frame without those 3 outlier points. And now let's go ahead and repeat this same scatter plot that I had before. And now when we repeat this scatter plot, you run this relationship looks like it's making way more sense. And these particular values, I don't mind too much anymore. They are showing some strong positive correlation and general trend that as you increase living area, you're also increasing sale price. Now, this is going to be much easier to fit to. Obviously, the issue that we had to overcome is the fact that I did just remove 3 houses from my data set. And who knows, maybe in the future, those houses are actually indicative of what is going to happen in this future real estate market. What I would probably want to know is when were these houses sold? If these kind of 3 outlier houses were the most recent houses sold in my data set, that should also ring alarm bells in your head because maybe this particular town or city is completely changing. And for whatever reason, maybe you have kind of like a Detroit after the Great Recession situation where even large houses are suddenly dramatically reduced in values. Lots of considerations to make here. And obviously, you're going to need domain knowledge for this particular data set in order to figure out what is reasonable to drop and what is reasonable to keep. So for our use case, we're just going to say, okay, we're going to drop those 3 points, and now we have a clean data set. Obviously, you could continue to explore this further, including more features and removing more and more things you deem to be outliers. Maybe you do want to remove these 2 points as outliers, but for our particular use case here, I'm going to say this is enough. We really just want to show you what is possible for removing outliers and an example of doing it. We don't want to spend here hours and hours of time removing every possible outlier for every possible feature. For the most part, this should be more than good enough. We removed 3 very troublesome points, and now we have a general trend that makes sense. Okay, finally what we're going to do is, if you want, go ahead and save this file. Make sure that you save it to kind of your own CSV file. So you could say something like df2csv, and then save this somewhere like data, and then kind of aims my outliers removed. Something I want to make completely clear to you is we actually have an official CSV where we already removed the outliers for you. So if you begin to type aims, you'll see that within the CSV data folder that you downloaded, there is already the dataset outliers removed. Do not overwrite that in case you accidentally mess something up here in this Jupyter notebook. Just go ahead and keep it as outliers removed. So if you want, you can save this, but we actually already have a saved version for you that we would recommend you use from now on. Okay, so that's it for this lecture. I hope it was useful to you to figure out just a couple of things to consider when you're going to remove or keep outliers. Thanks, and I'll see you at the next lecture.